Okay, let's get started on our second session this morning. And what we have on the agenda is we have two alumni from our optics program here at the UA who's going to tell us a bit about what they have done with their education in their career so far. And our first speaker is Cecile Chaix from Snap Incorporated. Over to you.
All right, thank you. So this is my first public speaking since my PhD defense, which was in 2015. So it's been a while. Hopefully I'm not too rusted. We'll see how it goes. I was thinking about what to tell you about what I do. Most of what I do is very secretive, so I cannot talk about it. But I still found a few, a few things to talk about that I think will give you an idea of what an optical engineer that works at a tech company does. And hopefully, when you hear about this, you may be able to see if that is something you are interested in doing or not. And then I will also tell you about how I got to do what I do today. So for the last 3 years, since 2016, I've been working at Snapchat. The company is now called Snap Inc., but you probably know it under the name Snapchat. Most of the company works on the app that maybe you use. It does a lot of fun stuff like putting filters on your face so you can send it to your friends, add a mustache, turn yourself into an alien. I personally like to use it. It's really fun. And for the last few years, small part of the company, about 160 people, have been working on developing hardware to complement the app. So some of this hardware comes in the form of sunglasses. This is our very first generation here. It's a pair of sunglasses that has one very small camera with a very wide field of view in one side. And it enables you to record pictures and videos that you can then load onto your app, modify a little, and share with your friends. The pair here is our most recent generation. That one came out in the fall of 2019, and this one has 2 cameras, one on each side, so that when you take a video, you can then do a reconstruction and build some 3D effects into them. I brought an exploded view of our sunglasses so that you can have a look at what it takes to make something like that work and how small everything looks like. I will not get into very details during the presentation on everything that's in there, but later on today, if you want to have a look, you're very welcome to do that. I also brought some cross-sections of the lens and the camera module so you can have a look at this. But basically, it takes quite a few engineering disciplines to get a sunglass on the market, a product like this. It takes mechanical engineers to design the whole structure, electrical engineers to design electrical boards that are here, thermal engineers to manage all the heat that is going to be in the system, and of course, optical engineers which design the camera module. So the optical team at Snapchat is very small. We are 6 people. We spend most of our time doing research and development for future products. So that is stuff that is going to come out hopefully 5 years from now. Then we spend some of our time developing the next generation, which should come out maybe a year or 2 from now. And also we do support for products that are currently in production. So if something goes wrong on the production line, we have to go fix it. So I'll go into a little bit more details on what I do at Snapchat on the camera module. To do that, I'll first tell you a little bit about how you develop a camera module. So it usually starts with a design team that thinks about what they want the product to look like, how they want people to use it, and they will come up with some requirements. So for example, they say we want to be able to see a field of view that is this wide so we can see our friends that are at this distance and so on. And then once they give us these requirements, the engineering team has to answer with engineering requirements and say, yes, we will be able to meet the field of view. It's going to be 115 degrees. This is the focal length the camera is going to have. This is the distortion, how it's going to look like. This is the relative illumination, and so on and so on. So we make a list of very long requirements, and based on these requirements, we make an initial design. And this is your basic lens design that you will learn about if you decide to pursue optical sciences. Once we have a design for a lens, we go talk to a lens manufacturer or lens vendor. Typically, these people are in China. That's where most of the lenses that are in your cell phones or on products like these sunglasses are manufactured. And we give them our requirements and our design, and they come back at us with their requirements, and they tell us this is everything we are going to be able to meet, and this is how the lens is actually going to perform once it's built. So there's quite a bit of a difference between what you design ideally on the computer and what gets built at the factory. Once we agree on the requirements, we tell the vendor, okay, go ahead, build them. Once we build, we need to start testing. So at the factory, we are going to run quite a series of tests to see if the lens performs well or not, and if we can use it or not. And then in Colorado, where I work, we are going to get a small portion of the production to do further tests. And those tests that we do in our labs tend to be like very long tests, so you don't want to spend 10 hours to test every single camera module, because if you're going to produce 10,000 or a million, it's going to take way too much time. So the tests you do at the factory tend to be really quick, and they are just a pass or fail test to see if the camera module is good or not. And the tests we do in our labs, those tend to be more implicated, and they are here to see what went wrong with the lens, if the performance is not met, or if it's performing exactly like we want. So this is typically once I start working on it. Not everyone does troubleshooting and testing. A lot of optical engineers work at the design stage or at the requirement stage, doing simulations and things like that. This entire cycle can happen multiple times when you build a camera for a product. Typically, your first shot is not going to be what ends in the product. It's going to take maybe 3 or 4 cycles before you have reached something that you know you can mass produce with an acceptable rate of success. So I'm going to give you 2 examples of what I do, specifically testing camera modules. And the first example, they both have to do with stray light. So stray light is basically all the light that is in an imaging system that you do not want. So it does not contribute to your image. And you probably have already noticed that in your own cameras. This happens when you look at a very bright light source. Sometimes you will see a secondary image or a ghost or a flare. So this is all what stray light is about. So what we want to do when we get a camera module is we want to see if the flare is acceptable. So if the image quality is going to look good, and if it doesn't, then we have to find a way to mitigate those flares. So how the flare arises, this is a light source here. This is the lens that we released in 2019. And if you look at the rays that are in red, this is like the path that was intended. So they go through the lens like intended, and they make this big blob here. And if you look at the rays that I have traced in blue and green, these will be reflected here on the back surface of this first element, and then reflected again on the front surface of the first element, and then make it through the rest of the lens all the way to the center, and they are going to create this ghost. So this is an example of how an unwanted reflection happens in a lens. It's very difficult to get rid of every single lens flare. So basically, when we test, what we look for are the ones we really don't want because they're unacceptable, they look terrible, and those are the ones we try to mitigate. These are 2 examples of lenses that are on the market. This is the one in the Samsung Galaxy S7. So this was the light source, and you can see a ghost here. This is the iPhone 7. The light source is here, and it has a very bright ghost right there. So this is just an example to say it's not just our lens that has lens flare. Pretty much every single lens on the market will have some. So when I first joined Snapchat, the way we looked for ghosts is we would receive camera modules, and then we would go outside and take a bunch of images, and then look at all the images and see if we saw something bad. And on this one, for example, here the sun was there, and it was pretty washed out, and on top of that we had this very bright flare right here. This technique for looking for ghosts was great because I got to spend a lot of time outside. The only problem was it was extremely time consuming. Sometimes we would miss some relevant ghosts because we don't have a feedback on the lens, so we just take pictures and then we have to review them later. It was very difficult to reproduce the results, so we decided to come up with a better way, and that is one of the very first projects I worked on was to find a way to replicate the sun environment in the lab. So I just designed this bench with a light source, and now it has some sort of blue sky around it. and a rotational stage with a fixture to hold some glasses, so we can move the point source inside the field of view. And you can see here are some examples of how that would look like. So you have your light here. The light levels is adjusted so that flares that tend to be washed out in the background on the blue sky will not show up, and only the flares that actually are very bright would show up. So you move the light source towards the edge of the field of view, you see some flare here, you move it at the very edge of the field of view, and you see this very bright ghost that we did not like and wanted to get rid of. We like this setup much better because it also enables us to be very precise when we go back to the lens vendor and we say, okay, we notice there's this very bright flare between 50 degrees and 65 degrees, and then they can do some simulations to see if they find them on their models, and then we can finally work on mitigating it. So another problem that we have with stray light is what happens when images get washed out. And basically, we had that on this lens that we were doing on the very first production. All the images we took were kind of washed out, which means the contrast was very reduced. And that happens when light from very bright region leaks into regions that are supposed to be much darker. So in the lab, to test that, this phenomena is called veiling glare. So it's a little different than the lens flare, but it's also a stray light problem. To test this, we usually take an image of a light panel that is very bright and has a very dark center. And this is what we want to see on our sensor. We want to see no light at the center, and then the relative illumination fallout towards the edge of the sensor. And when we measure the veiling glare, what we do is we measure the amount of light we have in a lit region and the amount of light we have in a dark region, and that gives you your veiling glare measurement. So for this lens module, it was incredibly high, and we didn't know where it came from. There are multiple sources possible for this. The first one we thought might be was that all our lenses are plastic lenses. So to manufacture them, someone has to make a mold. They have to polish the mold, and then they have to inject a plastic into that mold. And we were thinking maybe the mold was too rough and the surface of the lens was not smooth enough, and that it caused light scattering. So we spent a lot of time inspecting the molds, inspecting the lenses. Everything looked good. So we thought probably this was not the cause of the veiling glare. Another hypothesis that was possible, that one of the materials itself, instead of being clear, so letting the lights go through, like at normal incidence, it would just go through. Instead of doing that, it would be hazy, which means that some of the light would be scattered inside the material. This was a hypothesis that made us very nervous because if that is the case, we had no idea on how to fix it. So to basically rule out this hypothesis, I suggested that we make a model and that we answer the question, how hazy does the material have to be to lead to the amount of veiling glare that we measure? And I was thinking it will have to be very hazy, and obviously our lens is clear, so we will be able to rule out the hypothesis. So I set up a model in a software called Light Tools, which is one of the most used optical software for stray light analysis, and I ran a lot of simulations to see how hazy one of these materials had to be. And it turns out it does not have to be that hazy. And then we became very nervous because that meant this was probably the cause of our problem. So we went back to a lens vendor. We asked them to make us some flat blanks so we could have them measured for haze. And it turned out that this very first element came back with a haze that matched almost exactly what the model predicted. So we found what our problem was. It was a haze in material. It turned out the lens vendor, this was the very first time they were using this kind of material to make a lens. For them, it was a way to increase the range of lenses that they could make. So we had kind of taken a bet there that they would be able to do it. And we were very nervous because obviously they couldn't. So working with the lens vendor and the polymer vendor, so the people who actually make the plastic that you use in the lens, we were able to go back through the process and find out that they were actually not heating the material enough before molding it, and that caused the material to become hazy. So we ended up solving that problem, and the next camera came back perfectly clear. So that was great. So in summary, what I do at Snapchat currently is I pretty much troubleshoot anything. So I spend my time just doing that. And I was thinking about what does it take to troubleshoot something? What are the skills that maybe someone who is interested in troubleshooting would want to develop? So the first skill is to be able to formulate a hypothesis. So in the case of the veining glare, we knew that there were multiple possible sources, so those are our hypotheses. And then you need to come up with a way to test the hypothesis. So this can be either a hardware, an experiment, it can be a simulation, a model. And obviously, once you do that, you have to start thinking about how confident are you going to be in the data you collect or you generate to be able to validate or invalidate your hypothesis. So carrying out the test in case of an experiment sometimes is not as easy as you think. Observe and make conclusion. Often you will have to restart some of these. And then the most important part, and I think this is a skill that no matter what you end up doing, you need to cultivate, is to be able to communicate your findings. In the case of working in the industry, you no longer have to communicate only to people who understand exactly what you do. You also have to communicate to the program manager who wants to know why it was not ready 2 weeks ago and why you are going to tell them now that you cannot fix anything. So this is a skill I highly recommend you practice a lot. I say piece of cake as a joke. It turns out most of the time this is actually pretty hard. So I'm going to tell you a little bit of how I got there. So my early interests were kind of all over the map. I considered going into anthropology. I was interested in shepherding for a while, carpentry, pretty much a lot of different possibility. But I ended up doing what a lot of people do in France. After high school, I applied for engineering school. And this is a process that takes 2 years where you spend a lot of time studying before taking a competition to see if you can make it to engineering school. Some of the most useful classes I had at that time, besides physics, were classes in functional analysis and systems analysis. And if you're interested in engineering, I very strongly recommend you find a class like that. It will change the way you look at systems and you think about how machines work around you. I got accepted to a few schools, including the French optics school, Suboptique. I looked at the curriculums for each school. This one had something called quantum mechanics. At that time, I thought I wanted to do theoretical research in quantum mechanics, so I went to the school. And this was 15 years ago, and obviously you can tell I do absolutely no theoretical research in quantum mechanics. So what I learned in school there were mostly a lot of lab skills. And again, if you are going to pursue a career in optics, I recommend you learn how to align optical systems. Towards my end of school in France, I worked for 2 years at a very small company that was doing confocal microscopy. The company is called Monarchia Technologies, and it's called Monarchia Tech because it was started by 2 former astrophysicists who used to work in Hawaii and then decided to translate some of the skills they had learned in astrophysics towards medical imaging. And the reason I'm pointing this out is because I want to make it clear that sometimes you can decide to go in one direction and 10 or 20 years later find out that you may want to translate some of your skills into a different direction. One of the most useful things I learned at this company was how to document everything I do. And if you're going to pursue a PhD, I strongly recommend you learn how to write lab notes. So towards the end of my time at that company, I decided to move to Tucson to get a master's degree. Mostly I wanted to improve my English because I realized that people who have the most interesting jobs are the ones who can speak English. And at the time, that was not my case. I ended up really liking it here, so I stayed for a PhD. And I'll tell you very briefly about my PhD. I worked for Lars Fernlid in the Center for Gamma Ray Imaging group, building this system called it's an adaptive single photon emission computed tomography system. So it has 16 gamma ray cameras that are mounted on translational stages, so you can change the field of view and the resolution. It also has a very fancy pinhole aperture that can vary the number of pinholes it has, the diameter of its pinholes. So during this time, it was a lot of mechanical design, a lot of electrical assembly, a lot of plumbing, working with mice, the day I got my very first image, it was really nice. It took a long time to get there. So what I learned there mostly was how to troubleshoot, because on hardware, everything that can go wrong is going to get wrong at some time. So after graduating, I was totally burnt out on hardware. I never wanted to touch a piece of hardware in my life again. So I joined a very small company that was doing optical engineering services. The company was called 54Call. They were also doing optical modeling and software development. I got this job through the industrial affiliates, and the two people who actually hired me also had degrees from the optical science department. I was very happy at this company. I picked up a few lens design skills, much deeper understanding of trade-offs and optimization. It's crazy how different it is to design a lens when you're also writing the software that helps designing the lens. 9 months after I joined, we got acquired by Snapchat, and I was back doing hardware. So what I learned from that is sometimes you got to accept your fate. So here we are. So I have a few conclusions. Optics is very broad, a very exciting field. I kind of stumbled into it by chance, and I'm extremely glad I did. I don't regret it a single time. There's so much you can do that even if you think you may be interested in something today and then later you change your mind, that is also possible in the field of optics. You're also allowed to change your mind and try new things. That is one thing I learned during my PhD. I've personally found the optical science program at the U of A to be terrific, and I had an extremely great time in Tucson. I love the outdoors. If you love the outdoors, you're going to be really happy here. So, yeah, thank you very much for listening.
Of life as an optical sciences graduate.
That's a good way to get it started. Where's this gonna go? All right. Okay, hi everybody, I'm Zach. And yeah, I graduated from OpSci in 2016, and I'm just so excited to be back here and just wildly impressed with this program and with the stuff you guys are learning, and it's just amazing. Yeah, so the title of my talk is From Grad School to National Lab to Startup, and I think basically what I'm going to try to convey with this talk is how I wound up in graduate school and how I wound up working in a national lab, and just sort of the progress through my career so far. And the title of this talk is a little bit of a nod to the making of Star Wars documentary called From Star Wars to Jedi, The Making of a Saga, which is a video cassette, if you guys have ever seen one of those. They came in a box of 3 of the original trilogy, so that kind of dates myself, or puts a timestamp on my life. I had some music, but you can just imagine the Star Wars theme happening right now. A long time ago in a lecture hall, actually this lecture hall, not so far away, I was exactly where you are right now. I was visiting U of A for grad school. I heard a bunch of talks about the research that was going on here, and heard from some of the current grad students at the time. And so that was about 10 years ago. And what I can tell you 10 years later is that choosing to go to graduate school in optics or physics or engineering or whatever was one of the best decisions I've ever made. And I absolutely love my time here in Tucson, and I wouldn't have traded it for anything. So maybe I can just go back in time even further and tell you a little about how I got there. So this is Zach as a kid. I've always been interested in science and engineering, and I love building things. And I spent a lot of time playing with Legos as a kid. And there was actually another few pictures that my parents sent me in preparation for this talk of me playing with Legos, and some of them had clothes and some of them didn't. But apparently Tom already got to the showing babies without clothing, so I decided not to put that in. this is my Uncle Joe reader. He's a physicist. He, recently retired from NIST, but started working there in 1963. And he's one of my biggest role models. He's a spectroscopist, and I don't know if you can be famous for being a spectroscopist, but if you can be, he is. And it's because he's nominally responsible for the NIST spectroscopic database, which for an atomic physicist or for anybody that's doing anything working with atoms is a very important set of measurements. But he doesn't look like that anymore. That was actually a picture from his grad school lab in Berkeley in the early 60s. But now he looks like this. And when I was a kid, I spent a lot of time visiting him in Gaithersburg, him and my aunt on the two sides. And he used to take me to NIST, and he also ran a small company out of his basement called Optos Instruments, and they made vapor cells and microwave sources and all sorts of things for doing spectroscopy in universities and research labs around the world. So I really sort of, always in my head as a kid, had this idea that I would grow up and either be a NIST scientist or take over this company or something like that. This website is actually an HTML version website that I made when I was 11, but I had to go on the Wayback Machine because they sold the company, and they've since replaced the website and made it much better. So fast forward in time a little bit, I went to college. I majored in physics at Chaix Western Reserve University, and I'm thrilled to learn that I'm one of 3 Chaix or almost Chaix alumni, Jim Wyan, and I haven't met you yet, but I hope I'll talk to you soon. And side tidbit of information, the Chaix physics department, if you've ever been there, makes a point to slam you over the head with the fact that the Michelson-Morley experiment was done there. And so they have numbers of memorials, and there's even a descendant of the Isaac Newton apple tree on the Chaix campus. So I played tennis in college, and I spent most of my time either playing tennis or in the physics department, and I spent a lot of time doing undergraduate research in a condensed matter physics lab, doing crystal growth, and I, up until late in my junior year, I was firmly convinced that I was going to go to graduate school in condensed matter physics. But Uncle Joe, being an AMO physicist, said right around the early 2000s, there was a Nobel Prize awarded in atomic physics for the demonstration of a lab BoseEinstein condensation. He said, "Hey, Zach, there's this thing called a BoseEinstein condensate. You should go check it out. Go do a summer internship and learn about BoseEinstein condensates." So I did. I did a summer internship at University of Colorado in Boulder. And before I went, I learned a little bit about Bose-Einstein condensates, and I've sort of been informed that you guys are probably much more knowledgeable than I am at this point, after all the things you've learned this week. But essentially, if you're not familiar with them, a Bose-Einstein condensate is a state of matter where if you cool an ensemble of atoms down to very, very low temperatures, instead of having particle-like properties, they take on wave-like properties. And in fact, they can more aptly be described by the laws of quantum mechanics rather than classical mechanics. And even in some cases, you can describe the entire system of atoms with a single wave function. But what I didn't know about Bose-Einstein condensates at the time is that generating this state of matter takes an enormous amount of infrastructure. When I got to CU Boulder, I saw one of these labs, and the first thing I thought of is, well, that's Legos for adults. And the second thing that I thought of was, well, this is what I want to do with my life. This is the greatest thing I've ever seen. And these systems involve ultra-high vacuum chambers, laser cooling, laser trapping, magnetic trapping, all sorts of computer timing down to the microsecond level. So they're very complicated systems, and I got pretty excited about that. So this is a picture of me in the lab at CU, and another great thing that happened to me that summer was I met this guy named David, who became a really good friend of mine, and also came to grad school at U of A. So right after that summer was about where you guys are now, and David and I both ended up visiting a handful of grad schools, and we both came here for a visit weekend, and on that visit weekend, I met this guy. You may have already met him so far this week. That's Brian. And we talked at the visit weekend, and he told me about his lab, studying fluid mechanics in Bose condensed gases. And I thought he was the greatest guy I've ever met, and I turned out to be right. And I came to grad school, and I started working in his lab right away. And this is a picture of one of the BoseEinstein condensates in his lab. And the holes in the white density of atoms are vortex cores, which are tiny whirlpools that exist in these quantum systems that exhibit turbulence. So what's life like in grad school at U of A? Well, there's classes, of course. And we sort of, my fellow grad students and I formed, friendships over doing our homework for E&M class or quantum class or something like that. And we actually took a little liberty and did some of our homework on the windows on the 8th floor in the building, and got into a little bit of trouble for that. But otherwise, it was mostly harmless fun. But I was also involved in the student chapter here, which is a joint student chapter of the OSA and the SPIE, which are the two professional societies for optics. And I was very involved in the department. And one of the things that I'm most proud of with the time that I spent at U of A is I got pretty involved in educational outreach for kids. And we actually, while I was a student here, we started this thing called Laser Fun Day, which kind of exists apparently in perpetuity here. And it's a day where all these kids from around Tucson, a few hundred, come to the department and they see a bunch of demos about optics just to sort of get them excited about science and math and lasers and stuff like that. And I think this is probably a picture more for most of the faculty here, but there's one of Steve Jacobs in the middle. He died a few years back, but he was pretty involved in this stuff too, and he was always excited about that. So, I did a lot of, in addition to the stuff at the department, Tucson's a pretty amazing place, and when I came here, I fell in love with the desert. So we did a lot of hikes, and I visited the Grand Canyon with David, and this is the top right is an image of a backpacking trip I took with Brian and some of the other students in our group. There are a few field trips we took to some telescopes in the area. There's the Hobby Eberly telescope on the bottom, I guess that's your left. And then in the middle, the Large Binocular Telescope on Mount Graham. I think even maybe, Daewok, you may have been at that trip. So there are some fun activities associated with being a student here as well. So in terms of the research that I did, my PhD thesis was titled A New Apparatus for Studies of Quantized Vortex Dynamics in Dilute Gas BoseEinstein Condensates. And so maybe 3.5 years into grad school, Brian came up to me and he said, "Hey, I got some funding to start up a new lab. Do you want to start everything from scratch and build a new Bose-Einstein condensate system?" And I said, "Absolutely. That sounds like the best thing I could ever do." So I started with completely empty room. I even had my laptop set up on the ground on the left side of the room for a little while. And then we got a optical table delivered, and over the course of 3 years, we sort of built up this system. And even did a little time-lapse photography at one point. So this is a video of about 2 months of work that me and fellow grad students were doing on this new BoseEinstein condensation system. It's pretty short. But you can see how sort of involved it is, and all these electronics up on the shelf and vacuum system, and there's a bunch of laser systems in there and a bunch of people running around, so it's very exciting. And this is what the system looked like the day of my PhD defense. So from empty room to a decently built system, and now I've come to understand that it's much better than the state that I left it in, but I'm glad for that. And this is actually just a sequence of images, sort of a characteristic sequence of images, which shows the formation of a BEC, going from a thermal gas all the way down to this quantum state. And one of the things that you can see, so this was one of the first images of a BEC from this system, and it was sort of the thing that I'm most proud of, that we managed to get a BEC while I was still here. Okay, quick industrial affiliates plug. I'm not being paid for this, but if they want to, send a little extra check my way, it's not a big deal. That's my wife somewhere in one of the white suits, Laura. I met her at U of A. And that in the background is the James Webb Space Telescope. Well, Laura works at Ball Aerospace, which is one of the companies that works on the James Webb. And she got her job at Ball through the Industrial Affiliates Program, which is sort of it's a program where companies come in and get to know some of the students in the optics department. And I'm sure you'll hear about this if you haven't already. But it is extremely successful, and it works very well. And sort of when I was making this talk, I just went through in my head close friends of mine, where do they work, and from grad school, where are they working now? And this is a list of the companies, and you can see Google, Microsoft, Facebook. Cecile works at Snap. So this program works really well to connect grad students to industry and forward. But for me, I always sort of had research in mind. So after I finished grad school, I moved to Boulder, Colorado, and I started a postdoc at NIST, which is sort of the culmination of my scientific career thus far, was that I got to go work at NIST, which is, I think, one of the coolest places ever. And I started working on atomic clocks and miniaturized and portable atomic clocks. So an atomic clock, if you're not familiar with this, the idea is that all the atoms in the universe of a particular element are identical. So if they have a transition frequency, an electronic transition frequency from one atom to another, anywhere in the world, that transition frequency will be the same. So we can use an atom as a reference for an electronic or frequency, an electromagnetic frequency, and we can reference the frequency. So this is a picture of the first one of the first atomic clocks. It's NBS-1, which is the first cesium beam standard in the United States. But when I got to NIST, I started working on a different type of atomic clock. This is called a chip-scale atomic clock, and it uses the same atoms, cesium atoms, but accesses this microwave transition, the clock transition, in a sort of novel way. And what you can see is this clock is actually just about the size of a grain of rice. And here it's been incorporated into a commercial electronics breadboard. And this is actually the physics package here. And you can see that's just about the size of a microchip. So, these things are becoming more portable and more accessible. And one of the things, I'm glad the Event Horizon Telescope talk was this morning, because it teed up the topic of atomic clocks very nicely, and long baseline interferometry and things like that. Measurements rely on these atomic clocks. So making more portable and improved clocks is really important. So one thing you can do to improve an atomic clock, I'll probably speed it up a little bit, is to increase the frequency, and in that way you can record more ticks of the electric field per second. So this is the this is sort of one of the state-of-the-art clocks at NIST. It's in a terbium lattice clock, and I think Nathan worked on that as a postdoc grad student. So you have more famous alumni in the building. But I've actually been working for the past few years on miniaturizing these systems. So this is an example of an optical clock which sits on a matchbox size aluminum breadboard. And we have the whole optical clock system integrated onto this tiny little board. It includes a laser system and a vapor cell for atoms, which is housed inside a magnetic shield, which is the sort of gray box on the top left. And the whole thing is about the size of a quarter. So the other thing that I think is really cool, and I'm sort of out of time now, but the lab that I've been working on for the past 4 years is the same room that the last speed of light measurement was done at NIST in 1972. So there's quite a bit of legacy at NIST, and it's a very cool place. My friend David also moved to Boulder around the same time I did to start a postdoc at NIST, and he's been working on integrated photonic systems, which I found that you've heard about this week already. And he's actually been working on systems where the material that these integrated photonics are made out of have a nonlinear coefficient. So you can do nonlinear optics in integrated photonic elements. And these are two examples of taking a single frequency source that's pulsed and sending it through one of these integrated photonic waveguides and generating a full spectrum from the visible all the way out to the near infrared. And just in the last year, I sort of, the whole time I've been in grad school and at NIST, I had this thing in the back of my head that, what about Optos instruments? I still kind of had this thing where I wanted to start a company. So last year, David and I started a company based on some of the work mostly the work that he's been doing. It's called Octave Photonics. We shipped our first product out, which is this box on the top left, which takes in a single frequency pulse source and generates a broad white light continuum. We shipped that off to the Air Force in the summer. We delivered a second one later in the fall, and we just, towards the end of the year, got our first grant to do some R&D for this company. So that's all very exciting, and there's lots of, hopefully great stuff to happen with that in the near future. But I promised at the beginning that I would just say a few things about what I've learned in this process of grad school and a career in optics. And the first thing I've learned is that you have to always keep an open mind about new directions. There's so many exciting things to do research on: condensed matter physics, AMO physics, astrophysics, whatever. It's all really, really cool. And just because you're doing one thing now doesn't mean that tomorrow a new opportunity might come up in a totally different field that might be equally exciting and take you in a really cool direction. So definitely, keep an open mind. And the last thing is that, one of the best things about grad school is that the peers, the people around you, are all super smart. And in my case, most of them are smarter than me, but I've learned things from every single person that I've met in grad school and as a postdoc and my advisors and stuff, and it's just been an incredible journey, and my friends that I met in grad school have become my family, and it's pretty incredible to be a part of this whole thing. So I just want to end the talk by saying good luck. You guys have lots of really exciting things coming up, and if you need somebody to bounce some ideas off of, or say, like, what do you think about this professor at U of A? He's a terrible teacher, whatever. Don't hesitate to contact me. Here's all the ways you can get a hold of me. And yeah, I'm looking forward to meeting all you guys at some of the breakout sessions in the next couple days. Thanks.